All right, good afternoon. Couple of minutes late start here, sorry about that. All right, how is everyone today?
Good. How are you?
I'm good too. All right, well, let's see, what are we doing today? We're mostly doing interrupts, but let me make a few comments first. So first of all, let me remind you that homework 5, I moved the questions about timers to the following week's homework. So the homework that you're turning in on Tuesday is just on interrupts and things related to that. So you should have enough information, if not already, by the end of today to do everything on homework 5. Um, Homework 4, I graded and turned back, and that looked pretty good. I looked in detail at questions 49, 50, and 51, which were the questions about stacks. Um, Question 49 we actually did in class, right? Which was just kind of looking at the abstract idea of a stack. So instead of the push instruction from the pick processor, we were just looking at, draw stack, push a 10, push a 20, pop off the top, which is a 20, and so on. And so most people seem to do that fine. Um, Question 50, I wanted you to actually draw a picture of the pick stack to kind of compel you to look at it in the data sheet and think about, how deep is it? It's 31 locations that can store numbers, and those numbers that are stored are 21 bits wide, right? And then stack pointer is this 8-bit special function register that we've looked at. And 5 of those bits are the stack pointer, the thing that points to where in the stack, the top of the stack is. And then the other bits are flags that are used for like underflow and overflow. And then TOS is this 3-part register we've talked about, where since it's the value of the thing stored at the top of the stack, that's what TOS is. And since the stack is 21 bits wide, we need 21 bits of information there, while a single special function register only holds 8 bits. So we can't use just one, we can't use just 2 because that's only 16. We actually need 3 special function registers, and those are broken up into top of stack low, top of stack high, and top of stack upper. And each of these is a special function register, so it's 8 bits. And so 8, 16, potentially 24 bits of information. We only use 21 of them. So I wanted you to look in the data sheet and see those, and then just draw out a picture of that from table 5-2. When I ask you to draw something, don't just copy and paste table 5-2 into your homework, right? I want you to actually make a drawing of it. Because, like I say, it sort of helps you, recognize what's going on and puts it into a different coding in memory and so on and so forth. All right, and then question 51. Mostly people have got this. So the origin statements aren't executable code. They just say, origin 80 says call is stored at location 80. So at location 80 in program memory, we have this instruction which says call sub. All right, so here's the one thing that some people were missing. When you make a call statement, your goal is to remember where the subsequent return statement should return to. So if I store an 80, then when I'm inside my subroutine and eventually I say return, it would go back to 80 and it would call that subroutine again, and I'd be ping-ponging back and forth between 80 and the subroutine, right? So that's not what we want. And if I store the address of the subroutine 100, then when I get to this return statement, where does it go back to? Well, the only thing it's remembering is 100, so it would jump back to the subroutine, and I'd be looping forever inside my subroutine, right? What you really want to store when you make a call is the address after the call, right? So what's the address that we should go back to? Because the idea of a call is come down here to sub, do some stuff, and then when you're done, continue. And we continue not with the next instruction in your .asm file, because that's invisible to the CPU when you're running. We return to the next instruction in program memory. I'm obscuring my handwriting here, right? So we call sub, we do some stuff in sub. Where do we go back to? The next location in program memory after the call, right? So the call actually takes 4 bytes, locations 80 through 83, and so location 84, that's where we're going to return to. We don't happen to have specified an instruction for that location, but that doesn't make any difference to the CPU. All it knows is, hey, I'm at location 80, I'm doing a call, the next instruction should be at location 84. Before I execute that instruction, I'm going to jump down to sub, right, which is 100. I'm going to do all of that stuff, and then when I return, then I'll continue where I was, which was location 84. So one other detail here, and what I wanted to see here was the stack pointer and the top of stack registers after each instruction, right? And we talked about this a bit in class, right? So I really wanted to see, you know, here's my call statement. When that finishes, here's the stack, here's a stack pointer, here's the top of stack. Now I'm going to execute this increment. After that finishes, here's the stack pointer. So I wanted a picture after each of these instructions. A lot of people didn't do that. I worked with what you gave me. If I could tell that you knew what was going on, I let you slide on that. But let's take a look at this. So location 80, we're going to do a call. So what does our stack look like? Well, we don't know. We don't know what's in any of these locations. Location 0 doesn't exist. Top of stack is probably 0, but it's, you know, whatever's sitting at location 0, and stack pointer is 0. All right, after we make the call, what does our stack look like? Stack pointer gets incremented to 1. Location 0 is still unknown. Location 1 is hex 84. And top of stack is hex 84. So that would be your answer for what those things look like after you execute the call. And then we're down at location 100, which is where sub is. We do our increment. The increment does not affect any of this. But then eventually we say return. And after the return is done, what's the new value of stack pointer?
If it was already 0?
We did a call. Stack pointer was equal to 1. Top of stack was 84. This is what your stack looked like. Now we just did a return. So now stack pointer is 0. What is top of stack equal to?
Hex 82. Right?
So top of stack is always the contents of the stack at this index. So it's whatever is at location 0 in the stack. And location 0 doesn't exist. So we don't really know what that is. But we're not going to use top of stack when the stack is empty. Right? And the stack is empty because stack pointer is 0. But if you put 0 here, that's not a horrible answer. But let me ask you this. What is at location 1 in the stack?
Wouldn't it be, because you called sub at location hex 80, wouldn't it be hex 82 because it's a push for the next line followed by a go to, right?
Well, when we did the call, it pushed an 84 onto the stack, because that's whatever the next instruction is. Yeah, call is 4 bytes. So we pushed an 84. When we do the return, it pops that off the stack. It changes stack pointer to 0. top of stack to whatever's at location 0. The program counter will go back to 84. What do you think happens to the contents of location 1 of the stack?
Would it be empty because the stack pointer was only 1?
So that's what most people said. Most people left it blank or drew a question mark or wrote a 0. But what does it mean for a register to be empty? What does it mean for a flip-flop to be empty? Can a flip-flop be empty? Remember, these registers are just, 8 flip-flops connected side by side with their clock inputs tied together. So can you set that to somehow have nothing in it? This is a really important question. So what do people think?
Would it be just don't care values? Just filled with garbage, basically?
It's a possibility, but it's going to have some pattern of bits, some combination of 1s and 0s, right? It has no choice. That's digital logic. A flip-flop always outputs a 0 or a 1, or maybe it oscillates, but it's always putting something out on its Q output. And so 8 flip-flops is always putting out some bit pattern. And it could be garbage, but that garbage would have to come from somewhere. And some processors might fill this with garbage when you pop it off, but definitely not the PIC. And probably not most processors we encounter. So even though we've done our return statement, this hex 84 is still on the stack. But it's not considered part of the stack because the stack pointer is 0. And since the stack pointer is 0, we interpret this as saying the stack is empty. And we don't see this 84 on there. We pretend it's not there. But it's probably still there. In fact, on the PIC processor, it's definitely still there. And so even though we remove something from the stack, we don't actually remove it. What we do is we adjust our mindset and we say, I'm not going to see that thing anymore. There is no 84 on the stack, but it's still there. And this is really important because on other processors, we use the stack for more than just saving return values. We use it for local variables. We use it to when you're inside a function, you say integer I is stored on the stack. Right? That's done so that when you return from your function, the space you use to store your local variables goes away. But the values of those local variables is still on the stack, and it's still very much accessible. And this is a huge exploit opportunity. If you're not careful, if you had code that, let somebody type in a password and you store that password in memory, it was probably stored on the stack. And when you return from that function, it's still in memory. And a carefully crafted other process can come in and it can sniff those bytes out and it can read the values of your local variables. And so it's a definite security issue. So popping doesn't actually change what's on the stack. It just changes what we consider to be the end of the stack. In this case, the stack pointer 0, we say the stack's empty. But the values you had in there are still there. So that's just a side note to keep you awake at night. All right, let's see, midterm. So despite predictions otherwise, I did get your midterm graded, and I got grades and comments posted today. So those are available on Canvas. I don't want to take a lot of class time going over the midterm. By and large, I was really happy with the results. I think people did really well. Some of the grades may be lower than you were expecting or hoping, but the fundamental concepts in most cases are there, right? There's details that can catch you, but by and large, it seems like most people are on track. There are a few instances where I left you feedback saying, let's talk about this or let's go over that, right? And this is often cases where people have been having difficulty with the homework, and then they had difficulty with similar questions on the exam. Not terribly surprising, not terribly concerning if you course correct quickly. This is the end of week 5, so we've got 3 weeks after this. So you really need to, if you're having trouble writing conditionals, if-then statements, for example, you really need to come to lab today and pin this down so that going forward you can do these things. So I left you pretty detailed feedback, right? Question 1, a few issues with setting up tris A and tris B. If you're working on a question and it says you're connecting switches to pins 1, 2, and 3, how the heck do you know what those pins correspond to? There's only one way to know, right? You got to go to your data sheet. And if you go to your data sheet and you look at the picture of the chip, right, pin 1 goes to RA0, pin 2 goes to RA1, pin 3 goes to RA4. So our switches were connected to RA0, 1, and 4. And so this is port A. These are bits 0, 1, 2, 3, 4, 5, 6, 7. So we're using this bit, and this bit. So that's the first detail. And then once you know which bits you're looking at, you can go ahead and you can set up your tri-state register to make those inputs, which they are by default anyway. And then we said we had an output connected to pin 18. Well, what is pin 18? It's RB3. So if you look at port B, that's RB3, so that's the output pin. So you have to set up tri-state B to make that bit a 0. And then when you want to read your bit values, right, basically you can read from port A, you can use a bit mask. So if you AND port A with this pattern, that will give you an 8-bit number, which will be exactly, 3 zeros, followed by the value from switch C, 2 zeros, followed by the value from switch A, and the value from switch, B, and then A. And if you want to know if all 3 of those switches are turned on, is this equal to this binary pattern? And so you can subtract this, or you can XOR it if you like, and so on, and see if it's 0. And then if it's 0, turn your LED off. If it's 1, turn your LED on. How do you do that? Move a pattern, 1, 0, 0, 0. Move this to port B to turn it on. Move this to port B to turn it off. Or use your bit set, bit clear, or whatever. Remember, if you set up this bit as an output bit, you can't read it. So doing something like, an XOR to toggle a bit or something like that is not going to work. Doing an increment to change something from, all zeros to a 1 down here will not work. If it's an output pin, you can write to it, right? But don't try to read from it. I think that was pretty much it. And there's other ways you can do this, right? So some people did a series of 3 tests. First they tested this bit to see if it was 1, and then tested this, and then tested this. And if all 3 values were equal to 1, then they turned the LED on. Just make sure that you catch the opposite condition also. If any of these are 0, you want to turn the LED off. So make sure your loop is either turning the LED on or off. And some people wrote code that would turn it on when these were 1s, but didn't turn it off when these weren't, all 1s. Question 2, no real worries there, except the way answers were written sometimes. So let me hop in.
I actually had a question about that one.
Go for it.
So this is a problem I had in one of my other pieces of code too, and I get what you mean when you say that it'll just keep doing. If you don't have, it says to go to somewhere, right? and I have a branch that goes to somewhere.
I don't tell you to go to somewhere in here.
Oh, you don't?
No.
No, I must have just assumed that.
No, so you're writing code to do these things. So for example, let's look at question A. If num equals 0, num equals 9.
Well, yeah, but so the main question I had was, you're supposed to show this without having any sort of loops, because it doesn't ask you that, right?
Correct.
So how do you display that without any loops, but having it actually, have an if statement in there? Because wouldn't it have to go someplace else, but you would have to have it looping continuously in there?
No, so we can say move f num, right? Set the z bit. And if num is 0, we want to set equal to 9, so we'll say branch if not 0, no set. And here we'll say, set num equal to 9, so we'll move 9 into w, move w into num, and then down here is the no set instruction. And so there's two possibilities. If our number is equal to 0, right, we won't do the branch. We'll go ahead and we'll do this, and we'll end up here. If our number is equal to 0, we'll do the branch. Sorry, if it's not equal to 0, we'll do the branch, and we'll end up here. If it is equal to 0, we'll skip the branch, we'll put the 9 into num, and we'll end up here. So this chunk of code implements that, right? You come in here, you do these things, and whether you set num to 9 or not, now you're sitting down here, and whatever code comes after this statement, gets executed. The problem can be, let's say, move f num, and then branch if 0 set, and then here's, other code, and here's set. Move a 9 into w, move wf into num. Well, after this is done, it needs to go ahead and do this other code, right? And when this other code goes through, it needs to make sure that it doesn't inadvertently at some point go ahead and move a 9 into num. So you could put some label here, right? And then you could say branch to L, and you could that would work, right? But it's a little spaghetti-ish, but that's fine. So if it's 0, we come down here, put a 9 into num, and then go back up here. If it's not 0, we don't do the branch, and we go ahead and we continue this other code. So that would be fine. But that's not a loop, right? That's not going to force it to keep doing the same thing over and over and over again. That's going to, one time, look at the value of num, and if it's equal to 0, set num equal to 9. And if it's not, set num equal to 9.
But that's what I mean, is it's, so whenever I'm doing that, shoot, the comments that I got, it says that it would just continuously go down the program anyway, regardless of, so if it branches there, branch if 0, no set, it does go down to no set. But if it continuously and it skips that, wouldn't it just go down to no set anyway? Since there isn't any way for it to loop back up to the top.
This?
Yeah.
Yeah. So this code will end up down here whether it does num equals 9 or not, which is what you want it to do.
Oh, I got you. Yeah, I was thinking of, that's one of the ones I actually didn't get to.
Okay.
At the time, so I didn't get to that one. I was thinking of the other ones where it will go down there anyway, but that's not what we were supposed to do in that instance.
Yeah. So this is right, this is this block of code.
Yeah.
This is this label. All right, pop by lab hours if you want to talk about the specifics of what you wrote. We can go through it. All right, let's see. Question 3. Not a lot of worries there. I think minor issues. Comma 0 means put the value into the W register. Without a comma 0, it means put the result back into the file register. And I think a few people swap those in a couple of cases. Access bit, mostly correct. A few people got 1s and 0s backwards, which cost a few points, but I think you had the right idea. Convert the following into machine code. It's a clearf instruction. It's going to be 16 bits. Right? You can't write this with 20 bits just because there's an F here. That's the whole reason we talk about the access bit, because we want a 12-bit file register address, but we don't have 12 bits of file register in the coding for a clearf. Clearf is 6 bits of opcode, 2 bits for D and A, that's 8, and then we have 8 bits left to specify the file register. So the 8-bit file register we put in the instruction combined with the A bit makes this either clearf 90 or clearf F90. And in this case, if we set the A bit to 0, this 90 that we code in the instruction will be interpreted as F90. Everybody got the meaning of the D bit correct, I think, which was great. So yeah, D bit is the destination of the instructions operation. You have an operand that you're doing something to, and then you have, that's sort of the source, right? And then the result goes into a destination location. And the destination is either the same as the operand, the file register, or it's the special W register. So 0 means W, 1 means file register. So that was good. How many bytes program memory did the longest instructions take? That's 4 bytes. Call, go to, move FF are 3 examples. Give an example of one such instruction, so just tell me call, go to, or move FF. If you want to read program voltage, I think people got this one right pretty much across the board. So this is just setting up tris A and just setting up tris B. So if you're reading a voltage level applied to a pin, it's an input, you make the bit a 1 in tris B. If you're writing a voltage, you write the bit as, make the tris B bit as 0. Differences between branch and goto instructions. Okay, branch is different from BZ or BNZ. BZ, BNZ, those are totally different instructions. Those are conditional branches. But there is a branch instruction, BRA, which is an unconditional branch. And so this was really asking, what's the difference between the unconditional branch instruction and the unconditional goto instruction? But so many people said that branch can be conditional that I gave you credit for it. But that's kind of a statement on the instruction set rather than the branch instruction. So what are some of the differences between unconditional branch and unconditional goto? Let's hear your favorite examples of this.
The way they actually navigate the program memory. So like a branch will go to a position in program memory by adding the program counter plus 2 times 2 to the end value that you put in. And a go-to will do it by adding an offset, which amounts to multiplying by 2.
Cool. So the operating system lingo or machine language lingo would be branches are relative, go-tos are absolute. When you say go to location blah, blah is coded into the go to instruction. It's divided by 2, but it's the actual address you want to go to, right? When you say branch, you code in this magic number n, and then you do, 2n plus 2 plus your current program counter. So depending on where this branch instruction is executed, the place it's going to go to will vary. If I put a branch at location 0 that goes to location, 20, well, if I take that exact same machine instruction and I put it at location 100, it will branch to location 120, right? It's relative to your current location. Whereas a go-to is absolute. If I say go to 20, I can put that exact same pattern of bits anywhere in my program and it will always go to location 20. And that's a cool difference because it makes this code what we call relocatable. I could take the binary of my code and I could move it from location 0 to location 20 to location 100 to location 500, and it would still work correctly as long as all my branches are relative. But if I have go-tos, then it doesn't work. All right, we got a chat comment that said size. So a branch takes 2 bytes. Go-to takes 4 bytes. So that's another difference, different amount of memory. What else? Got at least one more.
we said we're only thinking about branch unconditional and go to, right?
Correct,
Not
yeah.
the fact that branches can be conditional
Correct, yeah.
versus go tos, which okay.
That is the difference, but there's one more difference between an unconditional branch and a go-to.
Distance they can travel.
Yeah. Right, the range of possible destination addresses for a branch is limited, whereas a go-to can go anywhere. So unlimited targets. And that's because of the relativeness. Good. There's actually one more difference. It's not one we worry about too much, but it's related to size. Speed. Because it has to fetch 4 bytes from memory for a go-to is going to take longer to execute. It's going to take an extra instruction cycle. Whereas a branch, it's a single instruction, 16 bits, 2 bytes, and so that's going to execute faster. Yeah, time it takes, perfect. So there's differences. How many general purpose file registers? 256. So there's a 12-bit address that we build for file registers using 8 bits of file register in the instruction and the access bit to add another 4 bits. So there's 12 bits of addressing, but the actual number of general purpose file registers we have access to is 256. And it's just those registers from 00 to FF. And then there's extra special function registers from F80 to FFF. But those are not general purpose. Those all have very particular functions. All right, and then 3 instructions that don't affect the Z bit. Everybody got those right, except I think for people who just typoed. But you go through table 20-1, move FF, your branch instructions, swap F. These things don't affect the 0 bit. And you can just look in that column of status flags and see what updates and what doesn't. All right, so let me know if you have particulars that you want to go over on the midterm. But like I say, I think most people did a great job on this, and if you ran out of time or something, right, that's it can be a problem, but it's a different kind of problem from, you know, I don't know what a PIC processor is or something like that. All right, so let's see. Let's keep going. All right, so I want to talk about interrupts. So go ahead and give me a quick attendance ping. Let me know that you're here, and we'll come back to this in a sec. I got to find my glasses. Alright, cool. If you want a fun service learning project next year, make something so people can find their glasses when they lose them. Because I think it happens a lot. All right, cool. Let's talk about interrupts in mplab. So we've worked through the basics of this already, but I want to dig down into some of the details. And I want to do this using mplab, and mplab is a great tool. It's for the most part, it lets us play around as if we had a physical chip. It lets us do things like set voltage levels on certain pins and see what happens. For timing, it's a little, leaves a bit to be desired, but for interrupts, it works really well. Alright, we'll get that back.
I had that in my lab a little bit with the delay circuit, or not the delay circuit, the delay loop that was included.
Yeah.
Where if I tried to run the program continuously, for some reason it wouldn't quite register my inputs and change according to them, but if I stepped through the code one by one, it always worked.
Right, yeah, and so my suggestion was for first approach is get rid of the delay loop, just put a breakpoint at the delay and put a return right after, so you don't have to loop through, 8,000 instructions.
That's what I was doing.
Okay, yeah. And the other option is just shorten the delay loop. Change that magic number 195 to like 1, and then it'll just loop through a few times, and you can see that it's actually doing the delay loop and then going back. Yeah, the simulation works a little differently when it's actually running. For example, it doesn't update your output variables, your watches, while it's running, but if you pause it, those should update. But it should respond to stimuli while it's running and do its thing. But we'll play with this right now. So so I have sort of plain old code here. It doesn't do anything. And what I want to do is just look at the intcon register. All right, so I'm going to include p18f1220.inc. Oh yeah, one feedback I gave people, and I've been giving people this feedback on homeworks also, don't define your magic numbers for port and tris and intcon and all of that. Okay, it'll end up biting you and your code's not portable and so on. Just include p18f1220.inc and all that stuff is done for you. Right, so get in the habit of doing that. So let's start at location 0, and I'm just going to say clear intcon. I'm going to spell it right. So we'll clear intcon. And then I'll go into a loop. And I'll just branch back to top of my loop. So nothing special going on here. Let's go ahead and build this, and let's go ahead and run this. And I'll pause it. And you can hover over your variables and get a little pop-up that tells you what the values of your registers are. But I'm going to use watch points here. So I'll go in here and I'll just type intcon. So we put a watch on that, and if I just sit here in the loop, you can see intcon is all 0, right? Well, I cleared it up here, and unless something happens that's going to change one of these, intcon's always going to be 0. So that's sort of what you'd expect. So let's set up a stimulus. All right, and I want to do a stimulus for for the int0 pin. So come over here and look at int0, and it's on pin 8, and that's also RB0 and also AN4. In the stimulus window, I can actually call it INT0. It knows about that too, but it's going to be the same thing as if I did RB0 or AN4. So let's set up a stimulus for int0. And I'm going to make a pair of these. And I'm going to make this first one an action which says set this pin low, and the second one says set it high. And so this is going to let me toggle my int0 pin in a very controlled way. The toggle button is convenient because, you know, it's just one thing to set up, but unless you know whether it's high or low, you can get confused and you end up chasing ghosts. So I like to set up a pair of stimuli, one to make the input low and one to make it high. Alright, so we can keep stepping this code and, you know, nothing's happening. Now what happens if I say fire int0 to be low? Nothing's going to happen. But if I fire the pin that says set int0 to be high, and now I step one step, guess what? My intcon register just changed. And this second bit changed to a 1. Now if I look at the intcon picture, what's the second bit? int0if. And that's the bit which says the int0 external pin interrupt has occurred. So by driving this pin high, this bit turns on to a 1. Alright, so that's our first connection between an outside event and something that we can look at in our code. Now if I go back and I rerun this, right, intcon is 0 again. If I set it to be high, my intcon changes back to a 1, 0. Alright, but nothing else is happening, right? The reason nothing else is happening is because we don't have interrupts enabled. But when you drive that int0 pin, it will force this bit to be a 1. Remember, this is an interrupt request. This is saying, hey, the int0 subsystem would like an interrupt. That's what the flag is. But if we don't enable global interrupts and we don't enable int0 interrupts, nothing else happens. It doesn't affect the CPU. We don't jump to that magic location 8 and so on and so forth. Alright, while we're in here, let's look at another interrupt flag, RBIF. So RB is an interrupt we can set to fire whenever any of RB4 through 7 change. And they could go high, they could go low, it doesn't make any difference. If they change value, we'll generate this RB interrupt request. So let's try that. Let's add another stimulus here, RB4, and I'm going to set this one to toggle because the claim is whether it changes to a 1 or changes to a 0, anytime it toggles, we should get this interrupt request. Right, so at least one of RB4 through 7 have changed state. So let's go ahead and let's step through this. And let's go ahead and toggle RB4. And guess what? Nothing happens. So even though RB4 is changing state, this bit's not getting set. Any ideas why? This took me about 5 minutes of debugging this morning. So let's try RB5. Let's set that to toggle. And let's step through. Remember, any of 4, 5, 6, or 7 should cause that RBIF bit to be turned on. So let's toggle RB5, and let's step the CPU. And hey, guess what? That least significant bit just changed to a 1. So when RB5 changed value, this RBIF bit got turned on saying, hey, something from RB4 through 7 changed state. But RB4 didn't do that. Any guesses why? I won't make you wait 5 or 10 minutes.
Could you continue once and maybe we can see if it changes back or anything?
So once it's set, it will stay set, but I can restart. And RB4 says RB4 has fired, definitely won't affect it. But RB5, as soon as I change that from whatever it was to the opposite value, that'll turn on RBIF.
What happens if you press RB4 now?
Well, we wouldn't see anything whether it worked or not, because the only thing that happens is this bit gets changed to a 1, but it's already a 1. And unless we clear but we could do this. We could clear intcon inside a loop. So let's build that and let's run it. And pause it. And so right here, let's go ahead and fire RB5. And so that makes intcon a 1, right? So it sets this RBIF. And if I fire RB4, well, we don't notice anything, but here we'll clear intcon. Well, that's surprising. Oh, that's very weird. Oh, I had this problem earlier too. Alright, let me try this once more. Alright, let's go ahead and set this. Alright, so there's a 1. Huh, that's very weird. This might be a glitch in mplab actually. Because I should be able to change that bit to a 0. That is odd and disturbing. But it's immaterial for the current question, which is what's the difference between RB4 and RB5. And so someone said they're getting treated differently. Does it relate to the pin's multi-purpose? Absolutely. So let's take a look at RB4. RB4 is sitting down here, and it's RB4, AN6, RXDT, and KBIO. RB5 is RP5, PGM, and KBI1. So the interrupt goes high, and it should stay high until you clear it. So the difference here, RB4 is also an analog input, AN6. And the default function of our input pins is to be analog. And the way we stop them from being analog, we make them digital, is we set up that ADCON register. And so all that's missing up here is our favorite piece of code. Put a 7F into W. And then move that into ADCON 1. So if we run this, and we step through, and then we try to fire RB4, let's toggle RB4. RB4 has fired. That will turn on our RBIF flag. So always set ADCON 1 to 7F, right? And in particular, when we're using int 0, for example, this pin RB4 has to be an input pin. When we're using RB1, int1, RB1 has to be an input pin. And if we're using this toggle when RB4 through 7 change, make sure you've set those up to be digital. So set addcon1 to 7F.
Can the pick do analog stuff?
It will, yeah.
Interesting.
So let's go through here and let's set RB4 high, and then let's toggle it again to make it low. So it went high and it went low again, but when we step the CPU, this bit still turns on. It still knows that this pin changed value, even though it happened in between clock ticks.
So the reason you were having an error there a second ago was because you didn't initialize addcon one.
Correct.
Right?
Yep.
Okay.
All right. So we can set these interrupt flags, but they don't cause interrupts to happen. Right? For the interrupts to actually happen, we need to enable the interrupt subsystem. So let's go ahead and do that. So let's have our interrupt requests interrupt the CPU. I can stop this. So we'll clear the intcon register for starts. We'll set up our digital inputs. And so what do we have to do to enable interrupts? First thing is in this IPEN, this RCON register, we want to set that IPEN bit. So come down here to RCON, and we want to set this bit IPEN. That enables two priority levels, high priority and low priority. So I'm going to say bit set file RCON, IPEN. So we enable high and low interrupts. All right. The next thing we want to do is we want to allow, let's just play with int0. Let's allow int0 to generate an interrupt. So we need to turn on this int0 interrupt enable bit. And that's in the intcon register. So I'm going to say bit set file intcon, int0 interrupt enable.
Are you allowed to do that? It set multiple bits at once?
I'm only setting one bit at a time here. If I used a bit mask, I could set multiple bits. I could just take, you know, what ones and zeros I wanted and move that into W and then push that over to intcon. Very error prone. So it's going to be cleaner if you do one bit at a time, because it lets you use, you know, these names like IPEN or int0IE, which match these things in the data sheet.
Am I missing something? How are you allowed to... Oh wait, never mind.
Got it?
I got it.
Okay, cool. All right, so we've got priority levels set. That's in the RCON register. We've enabled int0 to request interrupts, right? So int0 interrupt enable. Last thing we need to do, we need to enable interrupts at a global level. We need to say, hey, let's allow high priority interrupts. Let's allow low priority interrupts. All right, I'm just going to turn on the high priority one right now. So I'm going to say bit set file intcon global interrupt enable high. All right, you get the idea. There's two levels going on here, right? There's enabling int0 to ask for interrupts, and then there's allowing anything to ask for interrupts, right? This global enable says, hey, if an enabled interrupt requests an interrupt, go ahead and interrupt me. But this one bit, if we make this a 0, nobody can interrupt me. It doesn't matter if I turn on int0ie, rbie, timer0ie, right? If I don't have interrupts enabled globally, then I won't get interrupted. So this is enabling an individual source. This is enabling interrupts at all, right, globally.
Are we gonna have to move our initialization statements to a function and call it because we're sitting on program location hex 8 already?
You're
right?
absolutely correct. So if I were to run this code right now, let's go ahead and break things. So I'm sitting here and I'm looping and I'm looping and I'm looping, right? Let's go ahead. I'm going to get rid of these RBs so we don't confuse things. All right, let's go ahead and fire our int0 pin. And I'm looping, I'm looping, I'm looping. Oh, that didn't work. Let me try this again. Let me set it low and set it high. Okay. Well, I messed something up. So why is it not interrupting? What have we forgotten? We've got priority levels. We've got digital inputs. We've got int0 interrupt enable. Did I forget to rebuild? No. I'm having a moment here. Add con 1, int con, int0, interrupt enable, int con, global
I can't
interrupt.
get it to trigger the interrupt either.
Interesting. Oh. Yeah, okay, I'm being silly. Let's get rid of it, because I keep clearing my interrupt register down here. And so I'm undoing these bits that I'm setting up here. So let's get rid of that. And let's just make this loop nice and long. Alright. Build it up. Go ahead and run it. Go ahead and pause it. We're stepping through, we're looping, we're looping, we're looping. We're going to fire the int0 pin. We're going to step. And guess what? Suddenly we jump back up here. We're at this bit set file int con, int0ie. Alright. Why did we go there? Bit set file int con int0ie. That's this instruction right here. That's the instruction at location 8. So when you fire that interrupt, it's a high priority interrupt. What happened? Our CPU jumped to location 8. Well, that's not where we really want to be, right? Because if I do that, it's just, you know, in the middle of my setup and it's going to go back into my loop. We probably want to do something different in here. So yeah, so this is the earlier comment that we need to take this code and we need to move it somewhere else because we want to put, you know, our interesting code at location 8. So for example, let's make our interrupt handling code. And we'll make origin 8, and let's just say increment file hcount. And I'll define an hcount to be just some file register. So we'll make it file register 10. I do have to fix a few of my typos. Alright, so if I try to build this, I'll get all kinds of back talk. And it's going to tell me, basically, I'm overwriting previous address contents. right? And the problem is, I said this code should be at location 8, but since this code was at location 0, 2, 4, 6, this instruction was also at location 8. So what I need to do is put this code somewhere out of the way, like, I don't know, location 40. But remember, when we start the processor, it always starts at location 0. So I still need to have an origin 0. And what we want to do here is go to, let's just go to my setup. And this will be where we initialize stuff. Alright, you're allowed to do spaghetti code in assembly, it's going to happen.
I don't know what I'm doing wrong, but I'm following your code closely here, and when I trigger the interrupt, it goes to hex 12.
Oh, that's unusual. Should definitely not go to hex 12. Are you using a P18F1220?
Yep, P18F1220.
Is it going to line 12 or address 12?
Yes, line 12.
Oh, line 12. Go to your disassembly listing, see what that address is. It's probably location 8
Okay.
in memory. Alright, so what have we got here? We've got our program starting at location 0. It's going to branch to my setup, which is at location 40. It doesn't have to be location 40. It could be location 80. It could be location 212. But wherever this is, right, I'm calling this my setup. So this branch is going to go down here. I'll condition the system to handle interrupts, then I'll just go into this infinite loop. But when a high priority interrupt occurs, what's going to happen? I'm going to make a call to location 8, which is right here. So that's the interrupt handling code. And when we're done with our interrupt, we need to return from the interrupt. All right, is your code doing what you wanted it to do now?
What am I looking for in the disassembly listing again?
So for example, when I do this, it was going to, I think it was line 15. And if I look in the disassembly listing, line 15, this right here tells me that's location 8 in program memory.
Oh yeah. Okay, that's correct.
Okay, cool, perfect. Alright, so let's build this up. Let's run it. And I'm going to pause it. And as expected, I'm sitting here inside this loop. Let me add a watch point for my H count. So I'll put a watch at location 10. Right, and it happens to be 0 right now because it's a simulator. So I'm sitting here, I'm looping forever, I'm looping forever, I'm looping. Let me go to my stimulus and let me set my int 0 pin to high. And I'm going to execute one more instruction, and then suddenly I do a jump down to location at 8, right? INCF, H count. And if I look at my disassembly listing, my H count, my increment F H count, that's at location 8. So what happened? We fired the end 0 pin, our CPU jumped down to here, it's going to increment the value of H count. So this value, which is currently 0, should change to a 1, right? So it did the increment, and then we're going to do a retfie. All right, very interesting thing about to happen. We return from the interrupt, and guess what? We're back here at increment H count. Well, we increment the H count to a 2. We do a return from the interrupt, and we're back at increment H count. And we seem to be stuck in this loop. Every time we return, we increment the H count again.
I was having that problem too. I don't know why I was going back and forth.
Good question. Let's take a look at the intcon register. and it's a little hard to see on the screen probably, 0001 0010. That second bit, that 1 right there, that's the int0 if. When that bit's a 1, int0 is requesting an interrupt. Well, we're not clearing that bit out, it's still a 1, and so when we return from the interrupt, the system says, hey, int0 is requesting an interrupt, and so it jumps to location 8. It executes that, it does a return, and it says, oh, int0 is requesting an interrupt, and so it does another call to location 8. And so it's going to sit here and it's going to keep doing this. And so this is your next important lesson. Clear the interrupt flag. Right, int0 if, rbif, timer0 if, whatever it is that's causing the interrupt, you have to clear that. Now if I set my int0 pin low, that doesn't change anything. Right, this second bit of intcon, int0 if, is still set to 1. And so it's going to keep requesting an interrupt until we clear that flag. So usually somewhere in your interrupt routine, you want to clear that interrupt request. So I'm going to say bit clear file register intcon, comma, int0 interrupt flag. So let's clear the interrupt request. Let's build that. Let's run it. Let's pause it. We're in our loop. We're looping forever. Let's fire our int0 pin. So we'll fire it high. It jumps down to our interrupt handler. It increments h count. It does the retfie, and we're back in our loop. That's the behavior you're after. So we're hanging out in our loop. Interrupt happens. We jump down to location 8, do our business, return. We're back to where we were. Now if I fire this pin again, nothing's going to happen. Why? Because it's already a 1. So to make this work, I have to change this pin to a 0, which doesn't do anything, and then I change it to a 1. It'll usually do one more instruction before it processes the interrupt. So we're right here at this no op, right before the branch. And when we step one more instruction, it jumps down to our interrupt handler. So when it's done with the interrupt, where should it go? It should go right back here to line 23 where the branch is. So we increment h count. We clear the interrupt flag. You can see that 1 changed to a 0 down here. And then we return, and we return to the branch. Now if I fire my interrupt again, I go through one more instruction. I'm here at line 18. And now it's going to notice the interrupt, and it's going to do my call to location 8. We're executing instruction line 18 right now. So I jump into my interrupt. The interrupt, when it's done, should come back to line 19. Because that was the next instruction that was going to be executed. So we increment the high count, we clear the interrupt flag, we do our return from interrupt, bingo, we're back at line 19. So the interrupt always takes you back to the instruction that would have been executed next had you not been interrupted. Okay, that's another really key point.
Is essentially executing a call.
It's exactly executing a call. So it pushes the address of the next instruction onto the stack, and then it goes back. Incidentally, if you work on this with physical hardware, this business of setting the interrupt low and then setting it high, that does not work very well with a physical switch. Physical switches are bouncy. We talk about this a little in 250 sometimes. If I have one of those dip switches I slide from a 0 to a 1, it doesn't just take the input from 0 and raise it to 1. It'll actually bounce a bunch of times. And it's too fast to notice if you hook up an LED, but the processor will definitely notice. And you may find that your code goes into your interrupt routine, 3 or 4 times, even though you feel like you only changed the voltage from 0 to 5 volts once. Well, physical switches bounce, and so you can trigger multiple interrupts that way. That's not a problem on the simulator, though.
Could you just analog raise it in an actual test with like a power supply? Just increase the voltage until you hit the threshold?
That's a good way to do it. So you make a little circuit with a resistor capacitor pair so that the voltage slowly raises, and you put it through something called a Schmidt trigger. So when it exceeds some threshold, it outputs a 1. And there's hysteresis, so if it wiggles a little, it doesn't bounce.
Or you could do it like a potentiometer, maybe.
Those will be noisy too, probably. But these would be great experiments to play with, yeah. Yeah, because there's a critical point where you'd hit that threshold between a 0 and a 1. And that threshold might change. You know, the temperature changes constantly on the surface of the chip, and that might change where that threshold is and so on. What exactly did the message say? I didn't quite catch that. I don't know which message that was.
Mainly the retfie pop-up.
Sorry, say again?
The little blue pop-up in the top left corner for retfie. Extra note about retfie.
Just saying that retfie returns to the instruction that would have been executed next had you not been interrupted. So.
All right, that's good.
Yeah. So if we would have done this instruction but we got interrupted, that's where the retfie will return to. Is that another question coming?
Oh, no.
Okay, cool. All right, so we've got interrupts happening. They bring us down to our code. We can retfie from there and get back to where we were. Let's take a look at the stack action. So let's add a couple of more watches here. Let's add a stack pointer. And let's add top of stack low. Now, top of stack, remember, is 21 bits. We need 3 pieces, low, high, and upper. But all my code is sitting, you know, in the first few bytes of memory, so I don't really need to look at the higher bits of top of stack. I'm just going to look at those first 8 bits. So let's go ahead and just run this. And I'll pause it. Hello. And we're sitting here in our loop. Okay, so our stack pointer is a 0. Our top of stack is a 0. And let's go ahead and fire int 0. And, you know, we'll step once more. And we've got our interrupt flag became a 1. That's the second bit of int con. And when I step one more cycle, I should go into my interrupt routine. Watch what's going to happen. All right. Bunch of stuff just transpired. So my stack pointer changed to 1, and top of stack low changed to 50 hex. We pushed something onto the stack. What we just did was we made this happen. Right, stack pointer equals 1. Top of stack tells us what's stored in the stack at that location. That was 50 hex. So we know we have a 50 hex stored in this first location of the stack. That's the top of the stack. So that is presumably the return address. Well, let's look at our disassembly listing. And let's see what's stored at location 50 in memory. That's this no-op instruction. This no-op at line 20. So what just happened? We got an interrupt. The CPU said, hey, when you're done with the interrupt, I want to go back to line 20, location 50 in program memory. It recorded that fact by pushing a 50 onto the stack. And now if we step through a few more times, we increment our high count, we clear the flag, we do a retfie, where do you think it's going to go back to? Line 20, that's location 50. And we've got some red down here telling us the stack pointer just changed to a 0 and top of stack changed to 0. Because it just decremented our stack pointer back to a 0, showed us there's a 0 at the top of the stack. It popped that return address off the stack. So that's the whole call return business going on. Is this making some sense?
What were you using the top of the stack low for again?
Just to look at what that value is.
Okay.
So let's do this again. Let's step through our loop. And let's fire an interrupt. So I'll take it low and high. And our interrupt flag just got set to a 1. And now if we step once more, right, our stack pointer is a 0 right now. If we step once more, our stack pointer becomes non-zero. It becomes a 1. And in this case, top of stack low is 4E. So what happened, it just pushed a 4E onto the top of the stack. Right? TOSL is a way we can look at the value that's stored here. So this stack is actually 21 bits wide. And if stack pointer is pointing right here, we can see the value of this inside top of stack low. We can see the value of this in top of stack high, and this in top of stack upper. So it's a way to look at the action end of the stack, the thing that's actually at the top. And right now we've got a 4E pushed on the stack. Well, why is it a 4E? Because that's the return address we want to go back to. That's this no op at line 25. Sorry, at line 19. And so if we let it run through our interrupt routine and do the retfie, it comes back to line 19.
Okay, that makes sense.
Cool. All right, so that's the basic mechanics. And like I say, you can go into mplab and you can do these lab experiments of your own creation to sort of better understand what's going on with these things. And it's pretty consistent, other than the one weirdness we saw earlier about clearing the intcon register, which I don't understand. I think it's a bug. But for the most part, right, if you're writing legit code, you can actually step through it and you can actually see these things happening. And that can help with understanding and answering questions. So let's take a 5-minute break or 4.5-minute break. Send me an attendance ping. Let me know you're still here. And then I want to look at nested interrupts. I want to look at priority levels. Then I want to take a quick peek at the hardware that's making this happen. And then we'll talk about side effects. And then I'll touch on lab 4. So we'll be back in about 4 minutes. All right, we're back. Cool. Let's do nested interrupts. So, and we're just going to keep playing with the interrupt pins that we've already started with. So we've got int0, and that's a pin down here. We've also got int1, which is a pin 9, that's also RB1. So let's go ahead and wire up that. So I'm going to enable int1, and that's not in the intcon register, so we need to go to intcon3, and there's the int1 interrupt enable, there's the int1 interrupt flag. And so let's set those up. So, and generally you want to set up your interrupts before you do this global enable. Because once you enable interrupts globally, right, anything that is allowed to request an interrupt will interrupt you. So up here I set up int0, i.e. let's go ahead and set up int1. So bit set file, intcon2, int1 interrupt enable. So we'll allow that to fire an interrupt. And I'm also going to play with these priority levels. So int1 IP I can use to make int1 either a high priority or low priority. Now int0 is always high priority, but int1 I can make high or low, and the default value up here is a 1. So by default int1 is also high priority. So I'm going
Clear F, intcon2 up there at the top.
You don't have to. So, and I don't even have to clear intcon actually. I was just doing that initially just to get rid of these things I was doing, but we don't actually need to clear these at all because we're setting them up very deliberately, right? We're setting this bit, we're setting that bit. And so intcon2, this bit's going to be a 1 by default. If I clear it, then I'm setting all 8 bits to 0, and that's a little too heavy for me. So I'm just going to sort of tactically go in and clear this 1 bit, int1 IP. And so I'm going to say bit clear file register intcon2, comma int1 IP. And here's a chance to think about comments, right? I could put a comment here which says clear that bit of that register, but that doesn't tell the person why I'm clearing that bit of this register, right? If I know pick assembly, I know that whatever number this is and whatever register that is, it's clearing that bit in that register. But why am I doing that? Set int1 to be a low priority interrupt. So now when I come back, a year from now, and I'm taking a course at WSU and I'm trying to figure out what I did here, I can look at it, oh yeah, priority levels, I remember now. So I'm going to go ahead and do that, and then I'm going to go ahead and also turn on low priority interrupts globally. So now my system is armed. Low and high priority interrupts will both trigger interrupts. And so without doing anything else, let's go ahead and run this. Let's hang out. Let me add a stimulus for int1. And I'll make that a set low. And let's add one more for set high. Alright, so we're looping. We can fire int 0. Did I break something? Oh man, I broke something. Wonder if it's trying to save me from myself. Okay. I think I just needed to set this low and then high. Alright, so that's working fine. If I fire int1, weird things are going to happen. It's going to want to jump to a different location, location 18. And I don't have a location 18 set up. So I'm getting weird things going on here. So let's go ahead and write our low priority interrupt handling code. So we can call this the low priority vector. And let's increment a different file register, which I'll call lcount. And then I'm going to have to clear the interrupt flag for int1, which is also in the intcon3 register. So I'll bit clear file register intcon3 int1 interrupt flag, and then I'll return from the interrupt. So I'm going to make another definition up here for lcount. And I'll make that number of low priority interrupts. And let me add that to my watch list. Alright, let's build this up. Let's run it. Let's pause it. So we're hanging out here. If we fire int 0, we jump down to our usual high priority code. We increment h count, that's this number right here, so we've got one high priority interrupt. We go back to where we were. Now if I fire int 1, sad trumpet sound. Interrupt enable. I did the wrong register. Intcon3 is the interrupt enable, interrupt flag, and interrupt priority. So, and this is the kind of debugging that can take a really long time, but you got to look at your code faithfully, right? If every time I look at this, I say, oh, I'm enabling the interrupt, I don't see what the problem is, I'm never going to find the bug, right? So forget, what this is supposed to do. Go back and say, I want to enable int1 interrupts. Go back to your data sheet, int1 interrupt enable, that's that bit in this intcon3 register. Am I setting int1 IE in intcon3? And you can see, oh no, I'm not, I'm using intcon2. But that can be like really, really hard to find, right? Debugging C is hard. Debugging assembly language is about 10 times harder because almost nothing gives you an error when you actually assemble it. It's legitimate code, right? But it does something totally different from what I wanted. So be prepared to take some deep breaths, take some walks, come back and look at your code with fresh eyes. I've done stuff like this so many times and made mistakes like this so many times that it's a little quicker for me to see it because I know I make typos and such. So let's try this again. Let's run this. We're going through our loop. Let's just jump down and fire int1. And bingo, it jumps down to location 18. So this will increment our low count. That's that one right there. And then we go back to where we were. And we're back in our loop. And if I fire int 0, we jump down to location 8. And we do our thing and we return. Alright, so we got 2 interrupts hooked up. Let me make these interrupt routines a little more interesting. I think I made it too interesting. Alright, I stepped over from 8 to 18 by making it too interesting. Alright, so we've got our code. Let's run it. Let's stop in here. And we're sitting in our loop. Alright, I'm going to do the following. I'm going to fire a low priority interrupt, so an int 0. And I'm in my high priority handling code, location 8. And while I'm in here, I'm going to fire an int1 interrupt request. Alright, so a few things are going to happen here. I'm going to continue my interrupt code here at location 8. I'm going through, I'm executing my no ops. I'm going to clear the int0 interrupt flag. That just changed to a 0. I'm going to do a retfie. And when I retfie, suddenly I'm at location 18. So my retfie should have returned to my loop up here, but in the process of returning, the processor noticed, hey, int1 is requesting an interrupt too. And I'm no longer processing a high priority interrupt. I'm going to go ahead and process that low priority interrupt. So now I'm at location 18. I'll increment L count, clear the request, return, and now I come back into my loop where I was when the first high priority interrupt occurred.
Wait,
Yeah.
isn't this backwards? I thought it was, if you're in a low priority interrupt, you can be interrupted by a high priority interrupt. But if you're in a high priority interrupt, you cannot be interrupted by a low priority interrupt.
No, that's exactly correct, and that's what we just did. I started with a high priority interrupt, and then I tried to do a low while we were in there.
Oh, okay.
So yeah, you've got it exactly right. You just saw it backwards. But let's do it the other way now. Let's go ahead. We're sitting inside here. We're at the top of our loop. Let's fire our low priority interrupt. And we'll take a jump down to location 18. We'll increment the low priority counter. And while we're in here, let's fire the int0 pin. Int0 is high priority. We'll do one more instruction inside our low priority code. And all of a sudden, we jump to location 8. Now we're handling the high priority. We've temporarily suspended the low priority interrupt code. And now we're doing the higher priority interrupt, which is location 8. We'll go ahead, we'll increment our high count. We'll clear int0's flag. We'll do a retfie. Where's the retfie going to bring us back to? Wherever we were when we got interrupted. We were inside this loop at location 18. That's where it brings us back to. We finish that code. We do a retfie at the end of that. That's going to bring us back to where we were when we were first interrupted, which was in our main loop, where we're just looping through a top. So these things can nest. All right, let's do that same thing one more time, but let's look at the stack. Remember, right now our stack pointer is a 0. Top of stack is 0, so we're inside our loop. Let's go ahead and fire a low priority interrupt. And step 2 more instructions. We jump down to our low priority routine. Okay, our stack pointer is 1. Top of stack is 56. So I'm going to draw a picture of the stack, and I'll switch over to it in a second. So stack pointer is 1. And top of stack is hex 56. So here's what we've got. stack pointer changed to a 1. Top of stack low shows us the low 8 bits of the stack at this index. Index 1 must have a 56 in it. Why is there a 56 in our stack? Because if we go down to location 56, that's the address in memory of the instruction that we were about to execute. Thank you. You're welcome. That's the instruction we were about to execute when we got interrupted. So it's remembering where we want to return to. All right, so let's go ahead and start executing our low priority interrupt code. And now let's fire a high priority interrupt int 0. Step one more instruction. We jump to location 8. But take a look at our stack. Our stack pointer is now 2. So stack pointer has changed to 2. And top of stack is 1e. So here's what our stack looks like. Stack pointer is 2. That means this is the top of the stack. Even though it's at the bottom, it's an upside down stack. This is the top of the stack, 1e. That's where we should return to the next time we say return. After that, if we say return, we should return to 56. So it's remembering this hierarchy of return instructions. And it's saying when you next say return, jump back to location 1e. Well, what is location 1e? Look at your disassembly listing. 1e is right here. That's inside your low priority interrupt code. So when we get to this high priority retfie, I should jump back to line 45 and finish up the low priority code. And then when that's done, it should jump back to location 56. And location 56 is up here inside our loop. So we'll let it step through our high priority code. It's done the increment. It clears the interrupt flag. It does a retfie. Bingo, we're back to line 45. And as soon as that happens, stack pointer changed to 1. And the top of stack is 56. Stack pointer changed to 1. It didn't actually change anything on the stack. When you pop, you don't change the stack at all. All you do is change a stack pointer. But because that's a 1, that means this 56 is now at the top of the stack. And when we return from our interrupt, it should go to location 56. So we'll step through the remainder of this interrupt routine. We'll clear the file register. We'll say retfie, and we jump back to location line 25. And line 25 is location 56 in program memory. And now the stack pointer has changed to 0, which means our stack is empty. So that's kind of the whole like start to finish story of how interrupts happen. What happens when an interrupt is triggered? How does the system respond to it? How do you get out of the interrupt code? And what happens if you get interrupted while you're in your interrupt routine? And I strongly encourage you to repeat these experiments on your own, because watching is one thing, right? But it's really not a spectator sport. Get yourself a mplab session and put some code in and start going through these kinds of things and get to where you believe, deep in your soul, that if I fire this int 0 pin high when it's currently low, these things will happen, right? And once you're convicted that those things are going to happen, then you can start using those to do things like Lab 4, for example, or whatever it is. All right, I know that's a lot of stuff, but let me ask you questions up to this point. And as usual, lack of questions, I don't expect that to mean you understand everything perfectly. But if there's things that you want to ask about, please do.
So let's say I'm in a high priority interrupt.
Okay.
And a low priority trigger. Once I'm finish with the high priority if the, let's say, int1 is going to be the low priority interrupt.
Mm-hmm.
If it's still triggered, it's going to go after that low priority interrupt after I'm done, right?
Yep, absolutely.
Okay.
Yeah, so we can run this, we can fire, well, we could fire them simultaneously if we wanted. Like if both of these int0 and int1s went high at exactly the same time, we're still going to go to the, okay, just make me look bad. Let's try that again. And I've got a feeling I'm being a little sloppy with my clicking of these stimuli. Wow. Well, that's weird. Let me try this one more time. So let's fire both of those. All right, well, I told you the software is pretty solid, but actually I'm seeing some issues. Yeah, exactly. Because that high priority routine should have run first. So unless I'm doing something totally boneheaded here, which is always possible. But the way this should work, if you have both int0 and int1 requesting interrupts, int0 should get priority. And certainly if we go into int0 first and then fire int1, it will ignore int1 until int0 is finished. And then it'll jump down to int1. Actually, I have an idea what's happening. I think if you fire both of those at the same time, it gets confused. If you fire int0 and then do one instruction and then fire int1, it seems to do the right thing. But I think maybe the simulator is getting confused. Huh. I'll have to dig into that. But anyway, well, everything I've told you is correct. There's something funny going on in the simulator, but I'll dig into that after class. But yeah, so int0 will take precedence in this case, or anything that's high priority will take precedence. All right, so let's take a look at chapter 9 in the data sheet. And in particular, let's look at this figure 9-1. And this is kind of the answer to all questions that might occur about interrupts on the PIC processor. This one picture shows you kind of more or less everything you need to know. And so if you don't mind flashing back to 250, this is often the best way to answer questions. So for example, int0 IF and int0 IE go through an AND gate. So if interrupt enable is 0, int0 IF has no effect because the output of the AND is 0. If interrupts are enabled but the interrupt flag is not set, if that pin hasn't turned on that flip-flop, the output of the AND gate is 0, has no effect. But if you get a 1 out of this AND gate, you get a 1 out of this OR. Similarly, if the AD subsystem says you've got an interrupt enabled, you've got an interrupt request, the IF, and the interrupt priority is set to 1, then you'll get a 1 out of this line. This is the line saying, hey, the AD system is legitimately requesting an interrupt. And so most of these interrupts, int1, for example, if the interrupt flag is set saying the pin's, been activated, if the interrupt enable bit is set saying listen to those interrupts, and the interrupt priority bit is set to 1 saying it's a high priority, we get a 1 out of here. And all of these things go through various levels of logic, right? This is that IPEN bit saying that we're allowing priority levels. So that puts a 0 in here and so on. If all of those things are set, then ultimately what happens is you get a 1 coming into one of these. Those get ORed, you get a 1 coming out of here. That's the line that says, hey, something in the system is requesting an interrupt. And what do we do with that? We AND that with global interrupt enable high. If GIEH is a 0, all of this stuff is completely irrelevant, because even if you get through all of these different levels of logic and you get a 1 coming in here, this will block it. But if you have a 1 here and you have a 1 coming from your subsystem, you get a 1 out of the AND gate. This says interrupt the CPU, make a call to location 8. And if all of this stuff happens, if this is not happening, if you don't have a request for a high priority interrupt, but all of this logic down here says, hey, something with a low priority is requesting an interrupt, right? That'll generate a 1 here, and if you've got high and low priority interrupts enabled, this will go ahead and request a jump to location 18. So these drawings can be a little daunting at first, but it's mostly the same thing over and over and over again. This low priority section down here, well, if int1 is requesting an interrupt, if it's enabled, and if the priority bit is set to a 0, in other words, if int1 IP is 0 or the complement is 1, then we'll get a 1 coming out of here. And there's similar tables for the I/O subsystems if you want to see exactly what tris A and port A, how they relate to each other, how they interact with the I/O pins, and so on and so forth. Take a look at the chapter on the ports, right? So I/O ports, right? And you'll see this great picture here that shows you basically, what does tris do? Well, the tris pin, when you say write the tris register, it loads these flip-flops. And it loads them with 1s or 0s, and those are used to enable or disable these tri-state buffers, which take a latched value and send it to an output pin, for example. If this Q value is a 0, the 0 goes through the bubble, becomes a 1, this buffer will send the value of this flip-flop to the I/O pin. That's what makes it an output port. So it's worth, as you're going through these, coming back to these once in a while and sort of kind of scratching your head over them. We've even got some transistors in here, so how cool is that? And see if it helps or raises other questions. Yeah, it's a pretty complex chip. Certainly compared to a lot of what we've done in, say, 250. But yeah, definitely much simpler than something like an x86 processor with like a billion-ish transistors.
Close to the trillions.
Yeah. And part of the reason that RISC processors dominate the world of CPUs is because it's a relatively simple design. It's easy to keep making new versions of this. When transistors get faster, you can make a new version of an ARM processor relatively easily compared to a new version of an x86 processor, and so it can kind of ride that technology curve and keep things fast and cutting edge. All right, one more thing I want to talk about, and then we'll take a quick glance at Lab 4, but really quickly, side effects. interrupt-driven code can be really tricky to debug because, you know, where you are in your program when an interrupt request comes in can affect what's going to happen. And something different may happen if I get interrupted here than if I get interrupted here. Well, probably not, because these are just no-ops, you know. But if I had some interesting code up here and some interesting code down here, different things might happen depending on where I am when the interrupt occurs. And that can be really hard to debug. If you're finding strange things like that, where, you know, mostly my code works, but every now and then I interrupt and something weird happens, it breaks, it goes into an infinite loop, it resets the CPU, you're probably looking at side effects. And here's the idea of a side effect, right? When an interrupt occurs, you're going to jump down to, say, you know, coded location 8. Ideally, when you come back from there, you would like the world to look exactly like it did before you were interrupted. In other words, the only things that change in this interrupt routine should be the things that you want to have changed. For example, I want to increment the value of this high counter. So I'm going to say increment high count. I want to clear this interrupt flag, so I say clear this interrupt flag. But I don't want anything else to change. And if you're not careful, lots of things are going to change. For example, this increment instruction changes the z bit. After I increment h count, if h count is 0, my z bit will be set. If it's not 0, my z count will not be set. So suppose I'm doing something like this. So if x equals 0, go to ha. So I'm going to do the following. I'm going to say move f x. And I'm going to say branch of 0 ha. Suppose after I do this move fx, which I'm doing to set the z bit based on the value of x, suppose I get interrupted right here before I get to the bz. My interrupt routine runs. Let's say this is my interrupt code. What do? I increment file register h count. And h count changes from 7 to 8. Well, that sets my z bit to be, you know, not 0. And I do some stuff, and I bit clear file, and I retfie. When I come back here, my z bit is not based on the results of this instruction. It's based on the results of the last instruction in my interrupt code. And my branch is not going to do the right thing. And that's a real pain to debug. Because the code looks perfectly right. And most of the time when you run it, your code's going to work fine. But if I happen to get interrupted right between here and here, I might find that my z bit has changed in my interrupt routine. That's an undesirable side effect. And you always want to avoid undesirable side effects. Alright, so there's one pretty quick way to do that. And that's to use what are called the shadow registers. So there's you know, you have complete control over what happens in your interrupt routine, but inevitably you're going to end up changing status bits, right? So the value of the status register is most likely going to get changed, and that's going to mess up any conditional branches you have. So that's one thing we'd like to preserve. There's a good chance that the W register is going to get changed if you're doing anything, you know, slightly complex in your interrupt routine. We use the W register all the time. If you want to set something equal to 12, you're going to put 12 into W and put that into your file register. Bingo, you've changed the W reg. So we'd really like to save these, and we can do this as follows. We could say, you know, move file register status to something, maybe we call it status save. And then we could say move W to file register W save. So we could save these ourselves, do our interrupt routine, and then at the end we could say move W save back into the W register, and we could say move FF status save back into the status register. And then we could do our retfie. It turns out this happens often enough. We're always going to want to save the status register. We're usually going to want to save the W register. So when an interrupt occurs, the CPU does this for you. It saves the status, the W register, and actually one other register we don't worry about called the bank select register, BSR. It saves them. And instead of using file registers like status save and W save, it has a special set of 3 registers just for this purpose, and they're called shadow registers. And so when an interrupt occurs, your status is saved to a shadow register, WReg is saved to a shadow register, and BSR is saved. And when you return, when you do your retfie instruction, there's an optional argument, which is called S. And if S is equal to 1, that says take the contents of the shadow registers, load them back into status register, bank select register, and the W register. So if you do a retfie 1, it will always restore the conditional flags, the 0 bit, the overflow bit, and so on, and it'll restore the W register. But there's only one set of shadow registers. So if you have nested interrupts, this doesn't work. This only works for one interrupt. If you might be interrupted inside your interrupt routine, then you got to do something like this to actually save your registers yourself. All right, we've got -1 minutes to look at lab 4, so let's do that really quickly. And so lab 4 is kind of a hello world for interrupts. So there's a rehash of everything we've been talking about in the beginning here. It goes through some of the specific interrupt registers and so on. Make sure you look at all of that. Talks about returning from interrupts and so on. Here's an example code, okay? And this looks a lot like what we've been doing today. Location 0 goes to main, 8 goes to high priority, 18 to low. 20 is where our main code starts. We set things up. We set up ADCON. We make RA0, 1, and 2 inputs. Those are our int 0 and 1 pins. We set up interrupts. Again, try not to use PEIE, right? That's global interrupt enable low, right? We're not talking about peripheral interrupts, but it's the same value. So this sample code basically sets you up to receive interrupts from int 0, high priority, int 1, low priority. Okay, this is the stuff we've already done. And then our main loop basically just toggles this bit 0 of port A. So it uses a bit toggle, position 0. Uses the same decount code from lab 3 to wait for 1 second, right, 10/10 of a second. Calls delay and goes back up here. So this program, if we didn't know anything about interrupts, all it would do is just toggle bit 0 of port A on and off every second. But because we've set up interrupts and enabled them and done all this wonderful stuff, if while this code is running you hit the int 0 pin, what happens? You jump down to this high priority code, and the high priority code toggles bit 1 of port A, clears the interrupt flag, does a retfie. And the low priority interrupt code toggles bit 2 of port A, clears the interrupt flag, does the retfie. So the whole setup for this is, you're running your code, it's looping, it's toggling that least significant bit, but you can hit int 0 and toggle another bit. You can hit int 1 and toggle another bit. All right, so here's what you want to do in your lab. Make RB7 toggle every 10 seconds. Okay, so just, 10 seconds on, 10 seconds off. But if you hit int 0, toggle RB6 once. If you hit int 1, toggle RB5. If you hit int 2, toggle RB4. So it's an embellishment of this code. But my suggestion is, look at this sample code, go back and make notes on what we've talked about today, and come to an understanding of the interrupt subsystem, and then try to write your code to do these things. All right? And use the sample code not as a starting point that you modify, but, you know, if you get stuck, go back and look at this. But try not to just take this code and just tweak it to turn it into experiment 1. Right? You're going to learn this a lot better if you start from scratch. Take everything we've been talking about and try to write your code to do this. And use this as, you know, a helpful, related example of interrupts if you're stuck on something and you know, I can't figure out why this is happening, go back and look at this. All right, that's your whole lab, is just that one experiment. Have a test plan which says test when one interrupt occurs only and when multiple interrupts occur. And then all the usual boilerplate stuff, including a flow chart, right? So flow charts on every lab. And a new experiment. All right, we're 5 minutes past. Thanks for sticking around. Shoot me one more attendance ping, but everybody's still here, I can see. Hop into lab. I'll switch over to my office in a couple of minutes, and I'll meet you in there if you want to talk about midterm issues or questions on any of this stuff. Otherwise, have a good rest of the day, good weekend. I will see you Tuesday.
Thank you. See you Tuesday.
All right, thanks.